Hello everyone, welcome to Double Displacements. And the dance analogy for this one is pretty simple. You have two couples that are slow dancing, and then what happens is they decide to switch partners, and they end up forming two new couples. So this is the easiest one to do for word equations, okay? It doesn't get much easier than this. So you can think of it as the first things in both compounds are going to switch, or the second things. It's pretty standard to think of the first things are switching. So basically what happens here is sodium is going to want to switch with iron 3. Okay? You do not have to worry about if one is more reactive than the other, because remember, both of these elements are going to still be dancing or bonded to another element. So they're both going to form compounds. So we're not going to have the same issue that we did with single displacement. So it's literally, you basically erase iron 3 and you slap sodium there, and then you erase sodium and you literally put iron 3 there. Again, as long as they're on the product side, it doesn't matter the order. So I'm just going to go iron 3 chloride, and it's also going to form sodium oxide. It's literally that easy. Okay, it doesn't get much easier than this in chemistry. For the second example, zinc and magnesium are going to switch places. Okay, remember, the positive valence is going to switch with the positive valence, or you can think of it as the negative valence would switch with the negative valence. Okay, we don't want two positive valence things joining together, and we don't want two negative valence things joining together. So in this case, we are going to get zinc sulfide and magnesium fluoride. And it's that easy. Okay? Now, the tricky part is the formulas. So remember, sodium +1, chloride is chlorine -1. So when you crisscross, that's the formula I get. Iron has two valences, +2 and +3. The Roman numeral tells me I'm using the +3. Oxide is oxygen, it's -2. So when I crisscross, I'm going to get that. And then, in this case, it's fairly simple because I have the names already up there. But you can think of the Na and the F switching places. So the F is going to be dancing with the Cl. Now, iron, has a valence of +3. We know that because it was over here. Chlorine is -1, so when I crisscross, I get the 3. So it's not simply you're just taking the Fe, erasing it, putting Na there to give it Na2O3. Remember, every time you write a formula down, symbol, symbol, valence, valence, and then crisscross. And then sodium was dancing with oxygen, symbol, symbol, valence, valence, crisscross, and then that's what I would end up with. Okay? Now we have to balance this. And to balance this, let's see. I have 3 chlorines. But if I put a 3 there, that euchres me here because I have 2 there. So what I'm going to do is I'm going to make this 6. So if that is 6, I need 6 sodiums. 3 times 2 is 6. I have 6 chlorines. 2 times 3 is 6 chlorines. 2 irons, 3 oxygens, 3 oxygens, and then that would be balanced. Okay? If I'm going really fast on the balancing, don't worry about it because we've done enough balancing at the beginning of this section. You should be fairly good at it. I'm just speeding things up and not showing an inventory. Okay, for this bottom one, zinc, Zn, symbol, fluorine, valence, valence, crisscross, plus, symbol, symbol, valence, valence. They're going to cancel just to give me MgS. Zinc, +2. Sulfur. Sulfur's got a whole bunch of valences, but it's only got one negative valence. Again, the 2's will cancel. And then magnesium is going to be dancing with fluorine. +2, -1, crisscross. I'm going to get that. And it's balanced just the way it is. Okay? So that's kind of a standard one. And those are two examples that you can put down in your notes for that. Now, at the bottom of your note, there is a special type of double displacement reaction, and that involves solutions. So whenever you see an aqueous, remember that aqueous means dissolved in water. So water is present, and you've taken this substance, dumped it in the water, stirred it up, and then it ends up being dissolved. Okay? So we would have done an experiment on this at the end of the section. So what happens is you're literally taking two liquids. Now, these are not pure liquids, okay? You wouldn't put an L there. The AQ, again, tells you that it's dissolved in water, but I'm taking two solutions that are in the liquid phase, and I'm mixing them together. Now, whenever you mix apple juice, let's say an orange juice, assuming the orange juice has no pulp in it, you're going to get an orange-apple mixture, but you don't expect chunks to form in there, okay? So let's take a look what's going to happen. The first thing we have to do is we have to predict the products. So these are chemical equations, so there's no word equation for this. So the Na is going to switch with the Cu. Now, even as your chemistry teacher, I tend to do this just to kind of help me out on this, all right? So Cu is going to end up dancing with CO3, and Na is going to be dancing with SO4, all right? Now, I have to do my valences. +1, -2, crisscross, that gives me a 2. Now, copper has multiple valences. I'm really curious what valence I used over here. And I used the +2. And then sulfate was the -2. So I want to keep the same valence over here. And -2, they crisscross. And then that's basically all she writes on that one. Now, that's predicting the products, which was great. The next thing we have to do is we have to look at the solubility rules, which will be one of the attachments in with your note. And this is the solubility rules. So normally what happens on a test and on the exam, if you remind me, I end up putting this on there. But just because it's on there, you still have to be able to understand it. So you'll find that 1, 2, 3, 4, 5, the first 5 are basically telling you that, hey, if you have any of these compounds, they will dissolve in water. That's what soluble means. Over here, these are the exceptions. So as an example, you could have any nitrate, sodium nitrate, iron 3 nitrate. It doesn't matter. Any nitrate is soluble. It will automatically dissolve in water, and there are no exceptions. Acetates. Every single acetate will dissolve in water except for silver acetate. Silver acetate's the only one that won't. Chlorates, every single one will dissolve. Halogens, so chlorine, bromine, iodine, and even fluorine is in here. They are all soluble in water. Any compound that has them, unless you happen to be silver fluoride, silver chloride, silver bromide, silver iodide. Mercury 2 chloride, mercury 2 bromide, mercury 2 iodide, mercury 2 fluoride. And I think you get the idea here. Sulfates, most of them are soluble except for unless you are calcium sulfate, strontium sulfate, barium sulfate, lead 2 sulfate, or mercury 2 sulfate. Okay? Now, the bottom 4, these are compounds that won't dissolve in water, generally speaking. Okay? Here are your exceptions. So, if you happen to be ammonium sulfide, you're going to dissolve in water. Well, what are the 1A elements? Those are your alkali metals. So if you are potassium sulfide, you're dissolving in water. Sodium sulfide, dissolving in water. The 2A are your alkaline earth metals. So if you are magnesium sulfide, you're dissolving in water. Okay? So that's kind of how you read these. So how does that work and pertain to this one? Well, this is a carbonate. So carbonates don't dissolve in water unless you happen to be ammonium or an alkaline metal. That is not an alkaline metal, so that means that this guy is going to be a solid. This is going to be what we call a precipitate, and PPT is kind of the short form for it. If we did this, we would mix 2 solutions together, okay? This would be clear and colorless. This one is blue. and then we would have chunks forming. The chunks that are in there, okay, think of, and if you want, you can try it just to kind of get the idea of what I'm talking about. Take vinegar and milk and mix them together. Now that'll be gross, so if you have a weak stomach, don't do it, and certainly don't drink it. But what you'll find is the milk will curdle. So those curdles is a precipitate, okay? And then you obviously have the liquid part. So now we got to look at sodium sulfate. So sulfates are here. They are soluble. And then I just want to make sure that sodium is not an exception. It's not. So that means it will dissolve in water. So it will be AQ. Now, you might be wondering, well, wait a minute, there's no water in here. Don't forget what AQ means. AQ means you took some water and I threw some sodium carbonate in it and stirred it up. In another beaker, I had water and I took copper 2 sulfate, dumped it in there, stirred it up with water. And then I take those 2 separate beakers, I mix them together, and then now I'm going to get chunks forming. I'm going to have a whole bunch of water, and in that water, I'm going to have sodium sulfate. So that's kind of the tricky part on it. Now, people panic all the time because they're like, well, when do I do solubility rules? You have to have a solution and another solution, okay? Water has to be present. If water is present and I ask you to tell me the state, then you need to see whether the thing will dissolve in that water that was present in the solution. How do you know water is present? Either H2O will be mentioned, okay? It might be a reactant or it might be a product, or I can imply it by just telling you that you have a solution. All right, let's take a look at the other example here we have here. We have 2 more examples to go through. So in this case, potassium and cobalt are going to switch places. Now, what I tend to do, which helps me out here, is I just put the valences. Now, cobalt has multiple valences, +2 and +3. I need the 2. That's how that 2 happened. And -1. That kind of speeds up the process as I go through this. So potassium is going to end up dancing with nitrate. Symbol, symbol, valence, valence, crisscross. And then cobalt, we're using the +2 valence, is going to be dancing with hydroxide, which is -1, crisscross, 2. Now, be careful. If you have more than one polyatomic ion or radical, you need to put brackets around it. If you don't believe me, do this and tell me how many cobalts you have, how many oxygens, how many hydrogens, and then do the same thing here, and you'll see that there's a difference. Okay? Now, we have to look at our solubility rules. So our solubility rule states that nitrates are soluble. There's no exceptions. So that's going to be AQ. And then hydroxides. Hydroxides don't dissolve. And cobalt 2 is not one of the exceptions. So that means it will be the solid, and this guy will be my precipitate. So this will be the chunky stuff in our container if we mix these 2 solutions together. Okay? In the last example, hydrogen and magnesium are going to switch. Again, I would highly suggest you do the arrows. So hydrogen is going to be dancing with hydroxide. Now, that is the same thing as saying water, okay? It's the same thing. I know water is a pure liquid. Nothing's going to dissolve. Water isn't going to dissolve in water. It just forms more water. And then magnesium is going to be dancing with chlorine, symbol, symbol, valence, valence, crisscross, and I get that. Now, what I need to do is I need to do solubility rules. I just told you water is not going to dissolve in water, so I don't have to worry about that. I have to see if this is going to dissolve in water. The water that originally was there, plus I'm also making more water. Halogens are soluble, and this is not an exception. Magnesium is not an exception, so this will dissolve. Now, this is what I would expect from a grade 11 student. If you looked at advanced chemistry, instead of that, they will tell you that there's no reaction. Now, that seems like they contradict each other, because a grade 11 would say, sure it does, it makes water and magnesium chloride. What do you mean there's no reaction? Okay, now to help you out on this, I've done a diagram here to show you. So in the one container, before we actually start the reaction, think of these squares as beakers. I already have water in there, and then I've dissolved magnesium hydroxide. So I'm going to have magnesium ions and hydroxide ions. In a second beaker, I'm going to have hydrochloric acid. So I have water in there, and inside of there, I'm going to have hydrogen ions and chlorine ions. When I mix these two together, I'm going to get one beaker, and inside of that, I'm going to have water. Now, I've also added water, right? I'm producing more water, and then I'm going to have magnesium ions and chlorine ions. So pretty much what's happened is nothing has changed. Now, this is going to go a little bit above your pay grade because you might be going, well, Stan, what happened to the hydrogen ion and the hydroxide ion? I don't see them over here. So there was a change. Well, what water does, water breaks apart into hydrogen ions and hydroxide ions ever so slightly. So these guys are actually in there. Now, this is something that we talk about in grade 12 chemistry. So as of now, I wouldn't worry about that, okay? Here's another example I just made up. This one is maybe a little bit simpler to understand and visualize here what's going on. So I have sodium chloride and potassium nitrate. They're both solutions. So I flipped the sodium and the potassium, and I made potassium chloride and sodium nitrate. Now, nitrates are always soluble. There's no exceptions, so that's AQ. And then halogens are soluble, and potassium was not an exception, so that's AQ. So everything stays dissolved. So let's take a look at visually what's happening. In beaker 1, we have a bunch of water, and in there I have salt. So I'm going to have sodium ions and chlorine ions dissolved in water. In the second beaker, I'm going to have potassium ions and nitrate ions dissolved in the water. When I mix these two beakers together, in one beaker, I'm going to have a bunch of water, okay? And I'm going to have potassium ions that are still dissolved, and I'm still going to have sodium ions and chlorine ions still dissolved. Now, you might say, well, wait a minute. You formed sodium nitrate and potassium chloride, so it is a little different. But remember, they are dissolved. What does dissolved mean? Dissolved means that they separate. And we're going to be talking about this later on in solutions, but basically when you have a positive ion, now remember, water is a polar molecule. We talked about this, and this is very important for biology, particularly grade 12 biology, by the way. There is a slightly positive end and a slightly negative end to water. Remember, it's a polar molecule with a net dipole in that direction. So what happens is, when you have a positive ion, water will surround this ion with the slightly negative end, which is the oxygen end, surrounding it. And then the negative ion is going to have water surrounding it as well. But it's going to surround the negative ion with its slightly positive end, which is the hydrogen end. Like that. Now, normally what would happen is the positive and the negative ion would be attracted to each other and stick together. If that were to happen, then it wouldn't stay dissolved and you'd have a clump. But if it's dissolvable or soluble, it will allow water to pull a blanket around it. So almost think of a nail and a magnet. Normally they would be attracted to it, but then what you do is put a blanket around this and put a blanket around the nail and the magnet. What'll happen is those blankets will prevent the attraction from forming and they won't stick together. And that's kind of what happens here when you dissolve something. Again, we're going to be talking about this in section 10 and 11 when we look at dissolving. But these are some basic ideas that you really need to grasp, not only for chemistry, but you're also going to need it in biology. So for those of you that are like, well, I'm not taking chemistry again, but you are going to take biology, this is something that you need to understand when it comes to transportation across a semi-permeable membrane, which would be the cell membrane. Okay? So good luck with the questions today. And if you have any questions for me, make sure you let me know. Take care.